This is the Honors Geometry Semester Exam Review for Unit 2, Topic 1, which is questions 42 through 52. As like all the other videos, I just want to remind you that you're going to get this formula sheet on your exam and you really should use it. Just remember that it's there. Know how to use it for the exam. Again, it's not really going to apply to this topic, but I want to remind you of it anyways. Question 42. In the figure to the right, DE is parallel to BC. So we know DE is parallel to BC. We know that CE is 2AD. We know that AE is 8. We know that BD is 9. And we know that BC is 18. We need to prove that triangle ADE is similar to triangle ABC. So the first thing, I'm going to set up a two-column proof. So I'm going to have my statement and my reason. And the first thing I'm going to put is that DE is parallel to BC. And my reason for that is because it's given. Since I know that these two lines are parallel, I know that this angle is going to be congruent to this angle. And I know that this angle is going to be congruent to this angle because they are both corresponding angles. So we have angle ADE is congruent to angle ABC, and angle AED is congruent to angle ACB. And the reason for that is the definition of corresponding angles. All right, some of you might have used the reflexive property and said, so I'm going to put in an optional third step of angle A is congruent to angle A. And the reason being for the reflexive property. This is optional if you use the other two. You don't need to include this one. But if you use this one, you have to include one of these two to give you two angles. Because step 4, we can say that triangle ADE is similar to triangle ABC. And my reason for that is the AA, angle-angle similarity theorem. And that's our proof. Now we have to determine the length of AD. So I'm going to kind of do this on the side here. But I know that AD is proportional to AE. And I know that DB is proportional to EC. And that's the side-splitting theorem. So if I move this down, I'm going to have AD, side length AD is proportional to AE. And, AD over AE is proportional to DB over EC. Now, what do we know of that? We don't know AD, that's what we're trying to find, but we know that AE is 8, we know that DB is 9, and we know that EC is 2AD. So if we cross multiply, we're going to have 2AD squared equals 9 times 8, which is 72. So I know that AD squared is going to equal 72 divided by 2. So if I divide both sides by 2, which gives me 36. So if I square root both sides, yes, we have plus or minus, but we can take out the negative because you can't have a negative length. So AD is going to equal 6. So if I move back up here, I'm just going to put in 6 here, and I'm going to put in 2 times 6, which is 12. Finally, we want to determine the length of DE. Well, I have to take DE in terms of the small triangle and BC in terms of the big triangle. So I could say something like AD over DE is equal to AB over BC. Or I could do AE over DE is equal to AC over BC. Either way will give you the same answer. So I'm going to do AD over DE is equal to AB, which really is AD plus DB over BC. So what we have is AD, which we now know is 6, over DE, which is what we're trying to find, equals AD plus DB. Well, AD is 6, DB is 9, and then that's going to be over BC, which is 18. So what we really have is 6 over DE equals 15 over 18. If I cross multiply, I have 6 times 18, which is 108, equals 15 DE. So I can divide both sides by 15. And DE is going to equal 7.2. Jory wants to measure the length L of a pond. So that's right here. The figure below shows the measurements she will use to determine the length of the pond. In the figure below, AE and BD intersect at point C. Which similarity postulate or theorem may be used to prove triangle ABC is similar to triangle EDC? Well, if we notice, we have 20 and 40 and 25 and 50. So those are proportional, and we know that this angle is congruent to this angle. So we really have the side angle side similarity theorem. So what is the length of the pond? Show how you determined your answer. Well, I know that the sides are proportional, so I can pick either side. I'm going to pick 50 feet, and I'll compare it to its corresponding side of 25 feet. And then we'll compare that to L, because these are of the same triangle. So L over 30 feet, which is its corresponding side. So 50 times 30 is 1,500. It's going to be feet squared. Equals 25 times L feet. If I divide by 25 feet on both sides, what I'm going to have is 1,500 feet squared divided by 25 feet is 60 feet, which equals L. So the length of the pond is going to be 60 feet. Question 44. If two figures are similar, then corresponding sides are proportional and corresponding angles are congruent. If the two figures were congruent, then both these answers would be congruent. Question 45. In the figure below, triangle QRS is similar to triangle QTU. So we need to prove that RS, right here, is parallel to TU. So I'm going to do my two-column proof. Got my statement, and I've got my reason. And number 1 is going to be our given, which is that QRS is similar to triangle QTU, our reason being given. If two triangles are similar, then we know that their angles are congruent. All right, so we can pick one of these. I'll pick angle QRS is congruent to angle QTU. And my reason for that is corresponding angles of similar triangles are congruent. So we've proven that these two angles, angle QRS and angle QTU, are congruent. So finally, we can prove that RS is parallel to TU because if two lines, and I am going to run out of space on this because my handwriting, two lines are cut by a transversal, I did not mean the comma there. Two lines are cut by a transversal so that corresponding angles are congruent. Then the lines are parallel. So it's the converse of the definition of corresponding angles. And that would be our proof. Part B, write all congruences and proportions using the sides and the angles in the figure. So we know that our angles, Q is congruent to Q, QRS is congruent to QTU, and QSR is congruent to QUT. So we'll write that. Angle Q is congruent to angle Q. Angle QRS is congruent to angle QTU. And angle QSR is congruent to angle QUT. Now dealing with all the proportions. I will admit that there are multiple ways to write these proportions, but we're just going to talk about the general ones. For instance, QR is going to be proportional to QT. So QR over QT is going to be proportional to QS over QU. All right, so I'll write that. QR over QT is going to be equal to QS over QU. Another one is going to be QR over QS is going to be equal to RT over SU. Or I can look at it, QR over RT equals QS over SU. Either way, QR over RT equals QS over SU. Finally, we've got the third side. So we can say QR over RS equals QT over TU. Or we could say QS over SR is equal to QU over UT. So we'll kind of put it in terms of three. QR over RS is going to be equal to QT over TU, which is also equal to QS over QU. So again, there's different ways to write these proportions. I could say QR over QS equals QT over QU. I could also do the reciprocals of these. All right, same thing with all of these. So remember, proportions can be written in different ways, but they still should be talking about each of these three main ideas. 46. The figure below shows triangle BCD. Triangle B', C', D' will be the image of triangle BCD after a dilation with center B and scale factor 5. Complete the statements using the item bank on the right. So the point B' will be the same point as point, and we can say B, because the center is B. So B is going to map onto itself to give you B'. C', D' will be blank to CD. If you think about this, what you're really going to have is a bigger triangle. It's 5 times the size where this is B prime, C prime, D prime, because the center is B. So C prime, D prime is going to be parallel to CD. In the same token, B prime, C prime will be on the same line as BC. Finally, the perimeter of triangle B prime, C prime, D prime will be blank times the perimeter of triangle BCD. Well, if perimeter of BCD, triangle BCD, is 1, we know that we're going to be getting larger by a scale factor of 5. So it should be 5 times the perimeter. Perimeter of triangle B prime, C prime, D prime will be 5 times the perimeter of triangle BCD. 47. On the graph below, quadrilateral ABCD has been dilated, with the center of dilation the origin, then translated down 6 units to create quadrilateral A prime, B prime, C prime, D prime. So the first question is, what is the scale factor of the dilation? Well, I think the easiest one to look at is the horizontal DC and D prime, C prime. So if we look at DC, we can see that the length of it is 4 units. And if we look at D prime, C prime, we see the length is 6 units. So I want to know 4 times what scale factor of x is going to give us 6. If I divide both sides by 4, x is going to be 3/2, or x is going to be 1.5. And that's going to be my scale factor, 3/2 or 1.5. Either answer is fine. So then I'm asked, what is the ratio of the length of AB to the length of A prime, B prime? Well, if the scale factor is 1/2, 1.5, or 3/2, my smaller, which will be AB, is going to be for every 2 ABs, we're going to have 3 A prime, B primes. So the ratio is going to be 2 to 3. It's my scale factor. Finally, how are the measures of angle A and angle A prime related? Well, since they're similar figures, as we know because we've dilated it, the measures are going to be equal. Now notice it asks for the measures, so the measures are equal, but angle A and angle A prime are congruent. So the measures are equal, the angles are congruent. Question 48. Triangle ABC is shown on the coordinate grid below. Triangle ABC is to be dilated by a scale factor of 3, with the center of dilation, the point P, which is right here, of -5, -6 to produce triangle A prime, B prime, C prime. On the coordinate plane above, sketch A prime, B prime, C prime. So, we're going to use our idea of slope. So let's start with point B. Doesn't really matter. Actually, let's start with A. So to go from P to A, I'm going a distance of 1, 2, 3, 4. So for every 4 up, that's 1. I want a scale factor of 3, so I need to do that 3 times from P. So here's 1. Then we have 1, 2, 3, 4. Here's the second one. And then I'm going to go up 4 again. 1, 2, 3, 4. And I'm going to have A prime, which is going to be at -5, 6. So that's my A prime. I can do B by looking at slope. I'm going to go up 1 and over 3 to get to B. So if I go up 1 and over 3, I'm going to go up another 1 and over 1, 2, 3. So that's 2. And then up 1 and over 3 for my third one. So that's going to be my B prime at 4, -3. Finally, to get C, I'm going to be going up 4 over 4. That's 1. So 1, 2, 3, 4. 1, 2, 3, 4. That's 2. and up 1, 2, 3, 4, and over 1, 2, 3, 4. That is my C prime, which is at 7, 6. So these 3 points are going to connect, and we're going to have our new triangle A prime, B prime, C prime. And hopefully yours will look a little nicer and straighter than mine. Next, what is the ratio of the perimeter of triangle ABC to the perimeter of triangle A prime, B prime, C prime? Well, we know that we've got this scale factor of 3, and we know it's getting larger. So my perimeter, my perimeter for triangle ABC was 1, my perimeter of triangle A prime, B prime, C prime would be 3 times that. So my ratio would be 1 to 3. Finally, is there a sequence of rigid transformations that will produce the same result? Justify your answer. Well, hopefully you know that no, there is not. The reason why, so this is because this result, our triangle A prime, B prime, C prime is 3 times bigger than triangle ABC. But rigid transformations preserve size and shape. We say this all the time. So a shape can't get larger under a rigid transformation. And there you have it. Question 49. Quadrilateral ABCD has been dilated. The dilation results in the quadrilateral A prime, B prime, C prime, D prime. So we need to figure out the scale factor of the dilation and what point is the center of dilation. Well, let's start with the scale factor. You can take any one of these. It doesn't matter which one. And we're going to look at the original and then the larger. So let's say I took BC. To go from point C to point B, I'm going up 3 and over 3. So I'm going to look at how many times I can do that to go from C prime to B prime. So up 1, 2, 3 and over 1, 2, 3. That's once. Up 1, 2, 3 and over 1, 2, 3. That's twice. And then I can go up 1, 2, 3 and over 1, 2, 3. And that's 3 times. Therefore, my scale factor is going to be 3. And this will work with going between any 2 points. You're just looking at the slope and how many times you have to take the slope of your pre-image and do that to make your actual image. For what point is the center of dilation? We're going to take our points like A prime and A, and connect them, and I'm going to extend it out a bit. So that line is the direction for our A's. Now I'm going to apologize, this is not going to look nearly as nice as yours. You want to do yours with the ruler. But I'm going to be doing something like this for D's, something like this for C's, and something like this for B's. And I'm going to get this point right here, which is 5, 8. That point of intersection must be our center of dilation. So our center of dilation is 5, 8. Question 50. Pentagons ABCDE and FG, HI, are similar. So what is the value of x? Well, we know when we have similar figures, then the corresponding sides are proportional. We can figure out corresponding sides by using our given. So I want to find x, which deals with IH. I want that to be my only unknown. So I need two sides on here and two sides on here, one of which is IH, and therefore one that has to be, DC. So we can see IH is right here, DC is right here. So I'm going to pick BC over CD equals GH over HI. So I know that these are corresponding sides, therefore they're proportional. Now I'm just going to plug in. BC is 10, CD is 15, GH is 12, and HI is x. I'm going to cross multiply, so 10x equals 15 times 12, which is 180. Divide by 10, and x is going to equal 18. Next, I need to figure out what y is. So I'm going to take two of my proportional sides again. Remember, my only unknown should be y. So this time I'm going to take BC over DE and GH over IJ. They must be corresponding sides, but we have BC over DE and GH, which corresponds with BC, and IJ, which corresponds with DE. If I fill in the numbers, we have BC is 10, DE is y, GH is 12, and IJ is y plus 1.5. So I'm going to cross multiply, and I'm going to have 10 times y plus 1.5 equals 12 times y. If I distribute out, I have 10y plus 15 equals 12y. Subtract 10y on both sides, and we have 15 equals 2y. Divide by 2, and therefore we get y equals 7.5. Question 51. Jack wishes to find the height of a tree. He puts a stick into the ground and uses the sun's shadow to take some measurements. The figure below shows his measurements. First thing they want us to do is determine the height of the tree. Well, I don't know this height, but I know that this whole length is 135 plus 9, and then I have this little triangle, which is a height of 5 feet and a length of 9 feet. So I can take this triangle, which is similar to this triangle, and find my height. So I'm going to have 5 feet over 9 feet, which is my little triangle. And then I'm going to have my height of h feet, which corresponds with the 5 feet, and my total length, which is 135 plus 9 feet. What this is going to give us is 5 over 9 equals h over 144. When I cross multiply, 5 times 144 is 720, and 9 times h is 9h. Divide both sides by 9, and h is going to equal 80 feet. So I know that my height of my tree is going to be 80 feet. Then it wants me to determine the distance from the tip of the sun's shadow to the top of the tree. So it wants me to find this length, which is the hypotenuse. So I'm going to take, I've got my triangle, my big triangle. We know that the height is now 80 feet, and we know that the length, the other leg, is 135 plus 9, which is 144 feet. And they want us to find x, which is that length. So I'm going to use Pythagorean's theorem. A squared plus b squared equals c squared. A is going to be 80, so 80 squared, plus b, which is going to be 144, so 144 squared equals x squared. 80 squared is 6,400. 144 squared is 20,736. And the sum of those two numbers together is 27,136, which is going to equal x squared. I'm going to take the square root of both sides. I'm not going to use the negative because a length can't be negative, and x is going to equal 164.73 feet. So the distance from the tip of the sun's shadow to the top of the tree is 164.73 feet. Question 52. Draw examples of two triangles that are similar by each similarity, postulate, or theorem. So part A wants us to draw examples of two triangles that are similar by SSS similarity. So it really doesn't matter what your triangles look like. Here are my beautiful triangles. And all I need to know is that my triangles are similar by side, 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 meaning all of my sides have to be proportional by a certain scale factor. So I could literally pick a triangle that has sides 1, 2, and 3 and make up a scale factor, let's say 10. So this side would be 10, 2 times 10 is 20, 3 times 10 is 30. So here are two triangles that are similar by SSS similarity. All of my corresponding sides are proportional by a scale factor of 10. Next, I'm going to draw examples of two triangles that are similar by AA similarity. So again, I'm going to have my two triangles, and this one just needs to have matching angles. Corresponding angles have to be congruent. So let's say, I'm just going to make it up. This angle's 60 degrees. This angle's 50 degrees. So for my other triangle, if that's its corresponding angle, it's got to be 60 degrees, and its other corresponding angle has to be 50 degrees. And then we can say that these two triangles are similar by AA similarity. Finally, I'm going to draw examples of two triangles that are similar by SAS. So here are my two beautiful triangles. I need two sides that are proportional and the included angle to be congruent. So I'm going to pick, let's say, 10 and 20. All right, so those two sides, and I'm going to have an included angle of, say, 42 degrees. That corresponding angle has to be congruent, so 42 degrees, and my two corresponding sides have to be proportional, meaning that 10 times a certain scale factor has to give a number, just like 20 times that same scale factor has to give another number. So let's say 10 times 5. 10 times 5 is 50. 20 times 5 is 100. So these two triangles are similar by SAS similarity. And this concludes Unit 2, Topic 1 of the Honors Geometry Exam Review.